very much for inviting me. The talk I giving tonight is already presented a couple of times, once to the Auckland Structural Group. If any of your colleagues are interested, that's actually recorded by the Auckland Structural Group by going to YouTube Auckland Structural Group. Most of their presentations are recorded. Slightly different tonight, but in substance, it's recorded will be pretty much. So 8 years after commencing practice, the engineer was in court as a result of some flats that he designed. Foundations for the flats, which involved board concrete piles supporting the concrete floor and the concrete block walls, suffered settlement damage. Engineers' insurers decided and court held that engineer liable on the grounds that the design hadn't been complete until the building structure had been constructed. So in that exercise, I learned a couple of very powerful lessons. One, never do a foundation design unless you've got a comprehensive and deep soils investigation. I don't know if any people are involved in the sort of work I do, residential, light industrial, but common practice is just more hand auger down a few metres and scalers, and that's kind of it. But that is full of danger. Just done a review of a building in the Waikato where an engineer is going to be in trouble because they just did that. Now that one is sinking and subsiding. So insist on comprehensive and deep. It doesn't always have to be deep. It depends on the geology of the area. That was a very powerful lesson, and ever since insisted on that. Couple of years up the front. And the other thing I've insisted on is that we be engaged to carry out construction monitoring or observation, as it used to be called. I've made that a condition of my PS1s. They were called design certificates. Us carrying out construction monitoring since. It was painful, costly. It's a saying that a smart person learns from their own mistakes. A wise person learns from the mistakes of others. I gave a short talk at the last SESOC conference in 2019 on the lightning talk session, and that was titled Better Learning from Mistakes. And there I am, so the then chair of the Auckland Structural Group asked me to expand on that, so I did that. A bit about me, I'm not a specialist engineer, I'm pretty much general practice. Tell by looking at me, I've had some years of experience, a small practice initially in Hamilton and Auckland, so I've got 10 employees. I can concentrate now on low-rise structural work. Sometimes, notwithstanding what your insurers might tell you, there are some advantages in admitting a mistake early on, especially if the cost of fixing the mistake likely to be less than your excess. I've done this several times. Each time the clients reacted favourably. In one case, I made a mistake on some precast stairs, only half of what was required. Predictably, the stairs cracked as soon as they were put up. I admitted it, paid for the replacement. And I continued to act for that firm for over 30 years, had an excellent professional and personal relationship with that firm, and received many hundreds of thousands of dollars of fees since. And I'm still currently working for them right now. The background of what's happening, or I see is happening, in the structural engineering field at the moment. And in my involvement in the last few years, I've carried out more than 50 reviews, some of modern structures. Some were detailed, some were for expert witness for disciplinary procedures with IPENS or Engineering New Zealand. Some were high-level reviews. Some of them had a detailed review by other consultants. Some were as a result of people doing ISAs and low seismic ratings. One arose out of an assessment I did for a CPH applicant, and others as a result of working on buildings to retrofit, put in cranes and the like. And one to come to was a result of a partial collapse. More than half of those structures that I've reviewed had multiple significant and serious mistakes. It surprised me that many of the mistakes were the same or similar, even though the structures have been designed by different engineers from different firms. In spite of a comment or two made by some from New Zealand, a recent paper in the SESOC journal, none of them were for small or sole practices. They're all from mid-size and larger practices, including at least one national. These reviews were carried out at a time when structural engineers have been in the spotlight. And this started in the early 2000s with the open letter from John Scarry. Many of you may be too young to have experienced that, but there was a subsequent IPENS inquiry in 2003, and then followed the Southland Stadium inquiry, Royal Commission to the Canterbury earthquakes, collapse of some buildings in the South Island snowstorm, Masterton buildings, the report in Statistics House, and there have been anecdotal information about other projects that have had structural issues, including Vector Arena, Chartwell Shopping Centre, the CTV building, some named cases through the IPENS, Engineering New Zealand disciplinary process, including buildings that both Bob Hall and Stephen Ross were involved with. Recently, there's a report, the MD report on 230 High Street, Christchurch. Just recently, the Harrington Street car park building in Tauranga. And just the last few weeks or so, there's been some publicity about the earthquake assessment on the ANZ Albany building. This is a background to this. I've arranged to talk in a couple of sessions. Firstly, consideration of the significance of mistakes. We'll talk about the Swiss cheese model. We'll describe some of the building structures and some of the mistakes we found. I'll make some thoughts on why the mistakes may have occurred, opportunities we have from learning from that, and what we need to do to be able to learn from that. And the final part will be a shared presentation with another firm from came out of their peer reviews. This cheese model, many of you may come across this. The idea is that make mistakes, others. It's not until the holes line up that something is an accident or a loss. Now, for most of us structural engineers, that's going to be a severe environmental issue. It's likely in New Zealand, an earthquake or something like that. But those mistakes can be latent for years. Most of the buildings that I looked at were low rise, many were steel portal frames, concrete precast wall panels. Most of them were quite new, less than 10 years old. One hadn't even had a PS4 issued, it was that new. Some of those buildings are still subject to litigation and confidentiality agreements, so I've tried to anonymise the descriptions. Surprisingly, a lot of these buildings already had some design review, some internal, some external, some had so-called high-level reviews, part of the consenting process, including firms. So starting off with a statement, and sorry, I don't have slides on everything. There are a number of slides we'll come to shortly. So the first quite common mistake is wrong soil, working out your seismic coefficient. And we see this particularly, I see it often, engineers from out of town will come to Hamilton and decide for some reason that it's Class C soil instead of Class D. So you're going to do a job in an area that you're not familiar with. Local engineers or local geotech engineers, unless you've got access to specialist geotech skills. This is very common in ISAs. Next one, incorrect importance level. You need to think carefully about that. We viewed a medical centre, which is supposed to have been designed for IL3, didn't even come up to speed for IL2, sorry. Communication tower, normally designed for about an IL 1.5, would have been designed for IL4, suffered a partial collapse for a storm that was less intense than an IL1 event. Another communication tower strengthening we reviewed was designed for an IL2, should have been IL4, notwithstanding that it had police communications there. Ductility, very, very common. Designer uses or assumes a ductility, all the number crunching, but it's not matched by the detailing. All frames designed for ductility 3, detailing hasn't been consistent, inadequate number of poorly positioned restraints, and load paths for restraints. Parts design, now this was quite controversial until the MD Building Determination 2013, number 57, which clarified the intention of Section 8 of 1170, requirement for parts and components. So in practice, that means if you've got a full building and you've got wall panels spanning either horizontally or vertically, that the wall panels and their immediate supports, horizontal wailers or whatever, and connections need to be designed for parts, but not for portal frames. Yeah, I've encountered that quite frequently. Load paths just about always a problem. Mostly lateral resisting system, because you stuff it up for gravity system, you find out during construction. Still in eccentricities. Surprised a number of jobs where these haven't been considered, either modelling or analysis, trying to isolate the separate parts of the building. Structural support. There's quite a modern building. The dotted lines you see are the retrofit supports required for the 10-metre high panels. Another recent building, you see the panel on the far left, got no upper lateral support. Foundation. This is a tilt panel wall. See the dark outline is the additional retrofit building required. The sort of detail, the original details, one I've seen quite often. Think about it and look at it. It doesn't work. Foundations, and most of you will be familiar now with the findings from University of Auckland, Hogan and others on the use of inserts, the reed insert thing. We look at it there, taken out of their Strut and tie model. So these give very low capacities. I think the jury's still out in fact whether or not we should be using those. I think but that research is ongoing. Another one, people assuming base fixity without really considering what's happening, the deformations in the base plate and the board pile, and they're usually short soil structure for action. This is a very common detail for support, transom support or whaler support for a concrete precast or tilt metal. See there that the channel section really only clamped in place on one flange, little torsional or twist restraint, and most of these just have a simple fish plate, couple of bolts at the end where it connects to the portals. The problem is, the designer had us taken account of that, but they hadn't. They assumed it was fully restrained. I found that probably about 15 or 20 buildings, that same detail. The other thing on those panel connections is that very often they weren't designed for the actions under the parts provision. Roof bracing. Now that is not that good in that you can't really see the pool inside the pool here, but it's just to the right of where that brace is. So eccentric connection and not for reed type bracing, not designed for elastic as reeds say they should be. But the hard with these people not using the appropriate CS factor. Another eccentricity. There. One was the obvious one between the intersection of the braces and the strut. The strut itself has got an eccentric connection which hasn't been taken into account. All knees. I remember way back at university, and I was one of those ones that went to Ardmore. Historical event for most of you. And we did the exercise then, and we couldn't get these diagonal stiffness to work unless they were very thick. And I still struggle, and even looking at just some simple calculation on overstrength, flange forces, resolving them into the stiffener. In this particular case, which is a real case, it had a capacity of 684 kilonewtons. It's just the demand of 1,089. So I see these sort of details all around the place with maybe 10, 12, 16 millimetre plates, say a 460 EV or something like that. They're just not going to work. Thanks to John Sterry and Michelle Grant, we've had quite a lot of discussions on the appropriate ways to analyse. And that our analysis is simplistic. Jeff and people like him will know far more refined methods than that. This is a gable end wall. See that the purlins, bracket. Brackets fastened to the wall toolbox. A couple of issues. One is that the designers assumed the wall was propped. Okay, how does that work? Eccentricities in the purlin acting as a strut, connection. It's also got non-seismic rate, post-installed toolbox. Without it, it's not a good detail. Again, they haven't bothered to use parts. This is the remnants communication tower I was talking about. Top, almost half of it, 60 metre high tower, quite a significant structure. When I first walked on site, it struck me the bolts on the flange, the holes seemed small and not enough of them. Sure enough, when we came to do the reporting, that was the case. And then we were at the bolts were grade 4.6, so just inadequate. Of course, the failure mode should have been flange bending or some yielding rather than bolts popping. But sadly, that wasn't the case. This is one of those structures that was designed by 1.5. A whole lot of police antenna, TV, communications, vital communication stuff, so it should have been IL4. As an aside, we were engaged to do the retrofit. Foundations were anchored into the ground, post-tensioned, fused into block anchors. And because of the design, we had to do quite a lot of strengthening on the base. Luckily, the foundations, we ran tests on for the IL4 loads. What we found with the flanges, the only way we could get them to work was to use very thick washers, like 20 mil thick, to make sure that we could get that failure mode that we wanted. Sure that there were plenty of bolts to make sure we got the flanges yielding for the failure mode. Local wind pressures. Now I've seen lots of designs, and I'm guilty of myself, of not taking into account local wind pressure. Now, I've probably got away with it because I'm pretty conservative on the design of the purlins and the girders. So every job that's been reviewed, I've come away okay. This particular case, a very modern building, we retrofitted it quite extensively with the DHS fixed to the bottom flange. Another case, fairly uncommon, this one, down over reinforced wall connection. These were wall connections, single-story office building, designed as cantilevers for both in and outer plane actions, and cross-back connections to the ground. Because of that, they just had far too much reinforcing in the panels. They're going to give a brittle failure mode.
Can I just ask one question on that one? Sure. Are you saying wind uplift, so they didn't have stability on the bottom flange?
There's just not enough capacity.
Just not enough capacity even for downlift?
Yeah. Lack of roof bracing. Well, this one's quite hard to believe. The roof structure where the blue is not continuous, it's in a different plane. So it just doesn't, it's not continuous bracing. Another example is concrete block walls. Again, I'm not sure if the engineer designed them as a cantilever, they're inadequate for that. He designed them for a prop. There was nowhere for the loads to go back to part of the structure was braced. So I found design, and I'm no expert about this, but constantly coming across poor design or detailing and openings of diaphragms. I think most of you have been to Strut and seminar, which gives you some good tools on how to handle that. Mistake of mine, another one. A long time ago, I designed a farm bridge, the King Country, two-span thing. Here on the walkway. 3 years after it was built, piers leaned over because of flood debris here, and I made the fundamental mistake of not taking that into account, having either some sort of guarding structure or designing for those loads. Another one of mine, just a minor one, but it could have been serious if it hadn't been picked up by the reviewer. Using a live load factor for seismic loads for storage buildings. I was charged ahead using the 0.4 that I normally use, without realising it should be 0.6. Another one of mine, this is real confession time. Not that long ago, you see the full frame. Most of them have just got ordinary columns, but that one in the middle has got a horizontal beam going to 2 posts. This was discovered during the erection. That full frame went over a bit. And luckily, it was at that erection stage, so we were able just to pick up the braces and pull it back again. But I think that the important thing there for me is to always think about deflections, how your structure's deforming, and how different parts of them are deforming. All the frame restraints, and this is not that clear. You might see the greens where we put in additional flow braces. This is part of that building, the eccentric building that I showed earlier on. This was a bulk retail centre in a city. I came across it because of the initial earthquake assessment. We just completed a couple of $1 million worth of retrofit. Not just that, but you can see other stuff that wasn't very well. I can spend a little bit of time on this building. It's actually 2 buildings. Across the bottom, onto the floor, going up and down, there's another wall. See the bracing, the lack of bracing is the one from the previous slide. Ourselves and another firm of engineers carried out a detailed assessment of this one. Not sure if it's out of court yet or not. First mistake they made adopt a K mu of 2.25 to 1.25. Just a quick arithmetic writing down mistake. And in addition, for parts of the structure, they'd selected a ductility factor of 3, but failed to meet the detailing requirements. The transom beam, example referred to before, that reduced the strength to between 15 and 55%, what it should have been, depending on where it was on the structure. Steel full frames, enough bracing against buckling, not enough fly braces. Plates at the floor, for the example they used before of the base plates cast into the floor and assumed full fixity. The steel section that they assumed, the non-compact section, requires special consideration. So the strength of the frames vary between 26 and 60% of what was required. Concrete wall panels, one of those footings using inserts, footing connections, and the sizes not adequate. Again, reduced the strength to between 12 and 40% of that required. The roof braces were incomplete, so that got down parts of the building reduction to about 7%. The interaction with the adjoining building, you can see it's got 4 frames going in one direction, right-hand building, another direction, the left-hand building, yellow parts and mezzanine floors. They weren't taken into account. The eccentricities of the building. The right-hand building was built first, and the second building on the second, the whole property was owned by the same owner. So those things were repeated on both buildings, very low scores. Really 3D view of, I guess, why and how these mistakes being made. Probably a whole bunch of reasons. Some of the things that I think probably contribute include rushing to get a job out to meet a deadline or budget. I guess most of us have experienced that. I certainly have. You've got to get a deadline. You've got to get the job out. Skip, check, do a over. Inadequate quality assurance review, and that's often compromised by the rushing. Also, some of the QA peer review stuff and internally is sort of trends us towards tick box rather than looking at what's happening. This is on part of the review, looking at what's happening, the structural behaviour. For me, the wider use of computers and spreadsheets made it easier to do analysis, harder to visualise how the structure's actually behaving. For me, when I started off, we did distributions and things like that. Doing that, you got a really good feel for how the structure was behaving. It's carried me in pretty good stead since. So I think even simple check is just a bit of a look, just a few stick drawings. How you think the structure is going to behave, it's the drawing and the design tie up consistent with that. Another common cause of mistakes is using standard detailed or design practice that you've seen someone else use or another firm use without critical thought. And it may have been okay originally, often found that these are used in situations which just don't match up. For example, standard portal frame knee joints. How many of you have analysed a standard portal frame knee joint? None. Okay. Case in point, the actual behaviour is quite complex. Now, you might get away with it by using the standard era, bolting connections, but you really need to have a good feel for what's going on inside there. Insufficient fees. Now, a lot of you will be starting, I guess, to get into the area where you're not setting fees, you're giving advice to your senior engineers on how much you think it's going to take to do the job. Sadly, there's been a lot of fee competition since the Rogernomics era, and even though we weren't meant to, people have competed on fees. I started work a long time ago. Fee for an industrial building was 7.5%. But for industrial building, the building cost is pretty much construction. You get 80% for design and 20% for operation. You know, I hear now some fees less than 2%. Figure we were that lazy back then, or something not quite right. Training and mentoring. Sometimes I think people are pushed in the deep end without enough training and not enough mentoring. The final one is, and this appalls me, arrogance attitude of some engineers. These two of the cases that I've reviewed, the engineers were in denial for 2 years, and their responses were, I suppose rude would be a pleasant way of putting it. And I think some of you, if you were at the SESOC, the 2019 SESOC conference, there was a presentation given by an engineer from WSP Opus doing review work, I think, for the Wellington City Council. And he described some of the abuse that he got from engineers. The attitude of engineers is something that interests me in terms of its relationship with human factors. And together with Engineering New Zealand, they're shortly going to be announcing a series of seminars, or webinars, sorry, on lessons to be learned. One is scheduled for a couple of weeks and they haven't started publicising it, but they will be shortly. And the aim is to get people to share learning as a result of human failure, technical failure. So that introductory webinar, which I'm going to be part of, I'm going to talk a little bit about human factors and how they influence some of the mistakes that we see. So to learn about mistakes, first of all, we've got to know about it. For far too long in New Zealand, people have been hiding their mistakes. It's understandable because most of our insurers insist that we keep it quiet. There's also the shame factor. The example I gave at the introduction was the dress, one I never told anyone about until I gave my first talk at SESOC, the Auckland structure. So first off, you've got to know it. You understand the mistake and how it came to be and the nature of the mistake. You have to want to change. You have to do something about it, either change your own behaviour or whatever. How many of you belong to CROSS? Any of you? CROSS is Confidential Reporting of Structural Safety. Started in the UK, I think as a result of the aviation or NASA stuff, sharing mistakes on a no blame basis. Now, CROSS, Confidential Reporting of Structural Safety, in 2018, an Australasian operation. And just recently, I've been appointed as one of 3 New Zealanders to be on the panel of CROSS, where we assess the different reports. So I'd urge you all to subscribe to CROSS. Just go put in CROSS-AUS, get to the Aussie site, or if you just do straight CROSS, you'll get to the UK site. Join, it's free, heaps and heaps of useful information. Some of the British stuff is relevant to us, some of the British stuff, but I'd say at least 80% of it is relevant to us. And of course, a lot of it is to do with human failures. So one of the things that CROSS like to do in the aviation sector, and I spent 40 years part-time commercial pilot doing low-level operations and survey, and this just culture of reporting on a no blame basis Incidents and mistakes, certainly one reason why. Another thing I think we can do is to improve quality assurance, and I've already alluded to this. It needs to be a complicated thing. That's got its merits. I'll just keep a simple list of all the mistakes and issues I've found, and I use that as a checklist. External independent reviews are the ideal, most practical, or economical for smaller project. I think one of the marks of being professional is to share a mistake. It's going to be pretty hard, as I've already told you. So it's a good idea to share the mistakes, including those you find in the reviews. Sorry. That's the page of out of the UK one. They normally do about 4 or 5 reports a year. So what can we do? What can you do? First off, sharing your work. Share in discussion groups if you're a reasonable sized organisation. I belong to one in the Waikato. It's the early 1900s. We have a, they're not 1900s. We have a lunch meeting once a month, swap around, and there's about 9 or 10 of us that attend that. When I came up here about 15 years ago, we started the group. Rodney would meet morning tea on the first Friday of the month. And that group was led to the formation of a general practice engineering special interest group. Any who in general practice, that's a useful group. Share with your structural group, Auckland structural group. Write a brief article for the SESOC journal. Now, Stuart Hobbs, the editor, would love to have even a 2 or 3 liner about I learned from that. Subscribe to Hobbs newsletters. And try and promote just culture in your workplace. In Engineering New Zealand and SESOC. In other words, try to encourage a reporting, no blame basis of incidents and mistakes. And don't agree to confidentiality agreements unless there's a provision there to share the learnings on confidential basis. If you're doing peer reviews, regulated peer reviews, share some of the learnings. Years ago, Holmes Group gave a very good presentation to the Waikato Group, some of the learnings that they've come across in doing reviews to the Hamilton City Council. I understand a lot of the bigger firms and Becker's probably run in-house sessions, learning from mistakes, but I also have heard of a few that have ceased that because of problems with blame. Try and create that just culture. Share information. I'm going to, how are we running for time? We're okay? Yep. Now I'm going to share some information that comes from peer reviews by the HFC group. Some of the lessons that they've found. And some of the stuff is a little bit technical. Some of these items suggestions on how to avoid making the same mistakes. Some interesting detailing. Many things you can see wrong. 5 at least. Stiffness might be undersized. Size of the beams. Alignment of flanges and stiffeners, path. Might need some panel stone reinforcing strength. The quills may be undersized at 6. Welding details noted. The detailing, overhanging seems to be neglected by some people. So NZS 344, Chapter 12. So if we had a beam climbing into a column the same size, how many of the standard UVs would not require another height? At the moment, let's say close to 80%. And the same arrangement, standard UCs, say close to 50%, likewise none. This means that almost always you're going to need some panel zone reinforcement. Your column size is 2 or 3 times up from the beam size. For example, a 360 UV, then you can work with a 530 UV. Until you have 1.25 or higher, connections and load need to be designed. Capacity designed actions, either pull over strength or beam.
Just make a comment there too. Your panel zone, not only for strength, has a big influence on stiffness. So if your panel zone is even sized for strength, it has a big impact on your midspan deflection.
Thank you. Detail. It's fairly obvious there. This one is careful about modifying standard details. So I was putting in extra bolts, 350 plate, validate the original assumptions. So be careful about that. Don't design by guesstimating without evaluating the effect of the change. For thinking more bolts, more capacity, thinking thicker plates, more capacity, grade plates, more capacity. In some cases, you invalidate some of the governing criteria of the connection model. More bolts can even be governed by bolt capacity in the first place. For example, bigger or stronger plates, you may force the bolts to become critical failure mechanisms. Critical failure of that. How do we avoid issues? There's a few tips. Don't modify standard details if you can help it. Actually check and design any modifications, especially if you're pushing the capacity of the maps. Or the connection is part of a primary lateral load resisting system, and you're relying on understand the implications of changing various parameters. Be familiar with the design model. Don't play with it. It's always good to work out the capacity by hand a few times to understand the design model and get a feel for what you're doing. Always design to the minimum design actions from 3404 at a minimum degree robustness to the connection. So for the application of standard details, here are web plate connections designed for grade 250 plate. The web and plate is the 9mm. Threads are excluded, assumed for the bolts, particularly beams less than 460 UB, only for 8 plate. Welding for weld plates is designed to yield the before creep failure of the welds, so increasing the thickness of the capacity of the plate can easily validate that assumption. Here are tension compression splices are detailed for engineering, 250 plates. Introducing a gap for construction tolerances can invalidate the design now. So mostly you already come across fabricators saying, oh, it's 350. It's easier for them. Be careful. Plate grades. So what is the yield strength of an 8mm plate? It's 320, not 300. different grades again for hot roll sections. This is something that I have found fairly frequently in reviews. Just to make it different the strength of capacities. Angle design. 100 by 100 by 10 angle, 9.5 mil. The thickness of 160 50 or 6 mil. Just got to be careful of that sort of thing. And then for angle designs, if you're using the Australian Steel Institute standards, just be careful because the assumptions on ethnicity and things that's in excess of what New Zealand standard. Just cover it in the next couple of slides. Member restraint. It's a big one. Not good enough. Just to put in a fly brace in the roof or a floor or whatever, without thinking where are those loads going to? How are they going? How are they being transferred? FFC reviews said they find this quite frequently. So you get back to this principle. You've got to have the first off a restraint that's stiff enough for displacement. Depends whether you're talking about flexion or compression. Overall, you've got to have it going somewhere on a sky hole. A couple of slides on that. I'm not going to go into. Just be mindful of it. You know, it's really easy, I find, doing your analysis while you're chucking some fly braces, keep going. Where are they going? How are they going to get those actions? Restraint, this is probably something you're all familiar with. Stiff versus flexible, and happens with your critical buckling. One example that they found, people are relying on restraints. No basic example you may see more often in the Purlins, magically provide lateral restraint to beams, designing the beam for segment beam equal to the Purlins spacing. Simply adding a fly brace doesn't necessarily constitute a restraint. No load path provided. Reliance on lean-on bracing systems without meeting stiffness requirements to force higher modes of buckling behaviour. For example, using a dacian beam to resist the restraint. This can work, but only when the adjacent beam is approximately 20 or 30 times the minor axis stiffness of the beam. So we're still simply assuming restraints in the calculations achieve the capacity, but no signs of restraints on drawings. That's something I mentioned earlier on in my talk. When the member restraint, don't forget, the restraint forces accumulate. You need to take care of those. Now, this is a building that's probably going to be able to have time to go through it all, but that's the review they started with. It's the final reviews. Needs to be highlighted there. I think the next that picture there shows original consent drawings. As you can see, it's quite different. It's the sort of thing you really need to spend a few while studying through. But that's just to illustrate the sort of changes that have arisen from their peer review. That'd be basically so for me, there's one message I'd like you to take away tonight is firstly, admit you've made a mistake. Let's just want to hide it. wearing our tails between our legs. But don't do that. Share it. Talk about it with one of your colleagues or one of your groups. That way, I think we can improve the profession. Because if we don't do that, we're going to repeat the mistakes that we've made. There's quite a lot of evidence that there are intergenerational mistakes. 25, 30 years, a whole batch of the same sort of mistakes were made 25, 30 years ago. That's because the older engineers retire. Your engineers haven't made those mistakes yet. It's their turn. So, I think if we can, the library, share it, mistakes, that's an important thing. I think before you can actually freely share your mistakes, create a culture in your workplace or in your profession where it's not a shameful thing to admit a mistake. I think we can do that on the way to improve our profession. Get it, understand it, and learn from it.